Juan and Chris and all have just shown you how to build phenotypes, phenotype algorithms, cohorts, based upon some sort of definition. And when you build these algorithms, these phenotype algorithms, usually you're making it from something, and you're coming from some sort of case definition. So for MI, you might have a case definition for MI, and you're going to try to turn that into a phenotype algorithm that OHDSI, that Atlas can use. What I'm going to talk about today is how you can test those algorithms, because every algorithm, and Chris made a couple points about making your algorithms, your cohort definitions, which are basically based upon phenotype algorithms, making them more robust, and by adding in more features to it. Well, that's good, and you are making it more robust. You're increasing the specificity of the patients that you're bringing in, but you got to figure out what's the cost in sensitivity, how many patients you're losing by making it more and more robust, adding more and more features. So what we're trying to do is figure out a way to actually test our phenotypes to see how well they perform. And Juan gave some examples of how you actually test phenotypes, and I'll talk about the traditional way of doing it and how this sort of replaces it or augments it. So some of the things I'm going to talk about is why it's important and why do we need to test phenotype algorithm performance. And I'm going to talk a little bit, just maybe pick up a little time here, about a tool that we're developing to actually do that. And I can show you some of the results from that tool and evaluating a bunch of different phenotypes. So validating phenotypes, so when you and there's the question asked before on how do you get the definition for the cohort? And so you want to, if you want to publish something, you generally want to go to the literature and say what have a lot of other people used, because that's probably the easiest way to get something through a peer review. So you go out there and you'll see some definitions for myocardial infarction, how they actually defined it. And from there, you might use those definitions and put those definitions into Atlas. So one of the things that you'll do with definitions, and like what Sentinel has done, is taken their definitions and actually validated them. And a lot of groups have taken phenotype algorithm definitions and tried to validate them. And generally what you do to validate them is you look at some sort of clinical review of the patients who you say are in this phenotype. This is a study, this is a systematic review of myocardial infarction algorithms and the validation that went through it from Robo and Company. And they looked at 33 different studies. And what they found was that there was significant heterogeneity in the algorithms that people used, but also in the validation methods that they used, and particularly we'll see the difference in results that they found. So just stepping back a little bit on what it means to validate an algorithm. So in a table like this, where you're testing, you have a test and you want to test it against the truth. So in our case, the test comes from the algorithm. That's what you want to see how well you want to do, because there's different flavors of the algorithm. The truth comes from some sort of gold standard. One way that we've looked in the past is clinician validation. Of a group of people, a couple hundred people who the clinicians agree, 2 out of 3 say this person had an MI. That's the gold standard. And from there, you can come up with all kinds of statistics that say, if the clinician said this person had an MI and your phenotype, phenotype algorithm, your test said that this person had an MI, that's a true positive. They match up. And from there, you also see, if you said that this person, and your phenotype said this person had an MI and the clinician did not, that would be a false positive. And you also have false negatives and true negatives. And from there, you can calculate all the performance characteristics for your test. In this case, the test is the phenotype algorithm. Sensitivity and specificity, which are the basic characteristics of the test, but a lot of people also want to see the calculated positive predictive value. How well, of the people who you said were positive, what proportion of them were actually positive? So some of the studies that they looked at in the Robo paper, one of them was from Catrona, and this was from the Mini Sentinel program. And the test that they used was, their algorithm was based upon, remember this myocardial infarction, a ICD-9 code of 410.x or .x0, .x1 in the primary position. So this is the, so she added in a little nuance there, that in the primary position, meaning that's the reason for admission, and this is from a inpatient setting. So we have codes, we have that it was inpatient only, and that they had to be, the primary reason for admission was this code. So that was the test, that's the algorithm that they put together. The way that they determined the truth is that they took the patients and they did this, a bunch of cardiologists reviewed all the case records for these patients. So that was the truth as determined by these. And then they came up with the results of that. And they reported on the PPV of 86% for their phenotype algorithm. Another group, also looking at myocardial infarction, they used a little different algorithm. They used the ICD-9 codes of 410, but they enforced a hospitalization stay of 2 days or greater. So that was or greater than 2 days. So that was their algorithm. So they put in another nuance into there. They determined the truth by looking at, once again, going to a small set of patient records and looking at chest pain history, EKGs, things like that, everything that they could find in the record, and that's another set of clinician reviews. And then they came up with their results, and they came up with a PPV of like 93%. That was their result from their study. Another paper basically just looked at ICD-9 codes. They then found this, probably, looking deeper, it's probably ICD-9 codes and patients from inpatient hospitalizations. They also looked at to find the truth for these patients, they looked at the ECG findings and all the ancillary information that wouldn't be in the patient record, in the insurance claim record, for instance. And then they got the result of 76% for their algorithm. So similar algorithms, but very different performance. And what you see from this is a portion of what Robo had put into their paper, one of the tables. And you see these are the ones I just showed. One of the things you notice from there is that if you look at the N column, the N is very small. But also the range of PPVs, positive predictive values, go from 20 to 100. So using very similar algorithms, we see very different performance characteristics. So some of the conclusions that we could draw from this is that for MI, there's really no gold standard definition. People talk about phenotype libraries and things like that. You have to think about fit for function. When do you want to use different phenotype algorithms at different times? The process is very costly and time-consuming to go. As Juan said, you have to have clinicians review, and it's very expensive, and it takes a long time to do it. Plus, you can only do it for a certain number of people because clinicians will say, "Well, I'm done now. I'm not going to look at it anymore." So you get small sample sizes, and you have wide confidence intervals. The other thing that you can get, and this is a very important point, is that for the 33 studies, they all reported positive predictive value. But only 11 reported sensitivity and only 5 reported specificity. And the question is this really validation? So positive predictive value is an easy number to look at, and people say, okay, now I know what it means. Now I know how good the algorithm is. But the question is, do you really? So positive predictive value was given. Sensitivity and specificity are not given, generally because it's too hard, because you have to look at a much larger set of patients. For positive predictive value, you just have to look at the positives that you came up with, the 200 or 300 people, have the clinicians go through 200 or 300 and see how they did. Sensitivity and specificity, you have to include all the negatives in there to see how well you're doing. And that's tremendously high cost to do, and nobody's going to do it. The other thing is that sensitivity and specificity, though, are the actual characteristics of the test. positive predictive value is a function of sensitivity, specificity, and most importantly, the prevalence of the disease in the population. So, you might go through, and what this means is that you might go through and say, oh, I just picked up this algorithm from this paper, I'm using it, oh, and I know that it says it has a PPV of 90%, I'm good. Well, that's good if your prevalence just happens to be the same as the people, as the test that they did. And considering how they do these tests, it's not going to be. Probably all these have much higher prevalence than what you're ever going to get, because they're usually done at, maybe cardiovascular specialty hospitals and things like that. So you're going to have a much higher prevalence. So your PPVs are not going to tell you a whole lot. I mean, it's a nice number to look at, but... And I'll give you some examples on what happens with just looking at PPVs. So this is one test, one algorithm, and looking at two different populations. And we happen to know, through some magical power, that this test has a sensitivity of 75% and a specificity of nearly 99% plus. And let's say we're looking at a population of 10,000 people. If that population had a prevalence of 1%, you would get a PPV of 88%. So with that one test and a prevalence of 1%. If you use the exact same algorithm on a population that has a prevalence of 5%, you're going to have a PPV of 97%. So you see a very large difference in PPV just based upon the algorithm. And we see this in our data, where we have health claims data from people who are under 65 and Medicare data. And if you look at the prevalence of myocardial infarction, it ranges to, in the under 65 group, it might be about 1%. In the over 65 group, it might be 6 or 7%. So using the same algorithm, you can expect differences between them. Another example I want to show is that if you have one population, same prevalence, but we're looking at two different algorithms. But these algorithms you saw in the paper, they both had papers that they both had positive predictive values of 90%. So using one test, you could get your 90% positive predictive value, but you'll have a sensitivity using these numbers, sensitivity of 18%. Same prevalence, same test, but you could also for the 90% positive predictive value, you could also have a sensitivity with different numbers, but using these algorithms, sensitivity of 72% based upon so if all you knew was positive predictive value, you could have very different characteristics of the test. But we have to live with these algorithms because, as we're talking about before, we're going to use these algorithms to build our cohorts. So, and they're used in observational data all the time. So there's many different ways to build an algorithm for any of the health outcomes, and it would be nice to be able to know the performance characteristics for these algorithms. So validating these algorithms on any of our data sets using clinician review isn't going to happen. First of all, we don't have the records for large claims databases. And if we did, there's all kinds of bias in getting those records. If you talk to some of the claims companies, they can get a small subset, but it's a convenient sample of patients. It happened to be the ones that they happen to collect records for, and who knows how that relates to the actual population. It's costly, it would be ridiculously time-consuming, and the data is not available. So, once again, as we think about validating algorithms in observational data, we talk about the test coming from the algorithm, the truth coming from some sort of gold standard. So the question we had is there a different way to get to the truth? Since we know that clinician review is not going to be likely. And one of the things that we're working with is to do diagnostic predictive models. And this uses, within the OHDSI community, this uses the PLP package that Jenna and all have talked about, and we saw some examples yesterday. So instead of prognostic models that are looking to the future, there's also a way to look at diagnostic models to be able to tell you At the end of the day, what a diagnostic model does is gives you it looks at a set of data and gives you the probability, similar to what Juan had, of the person having that disease. So the way that we're doing it is we find a gold standard of subjects in the health outcome of interest. We develop the predictive model. We apply that model then to the population. So what you have at the end of the day with a predictive model is that you have a model based upon characteristics within the data set and a set of betas associated with it that you can then apply to another population and use that model to give a probability of, in this new population, what's the probability of any one person having that disease based upon that model. So we apply the model to the general population. We set some sort of cut point. Juan had said something like 95%. Is that somebody trying to get it? He said something like 95% or 50% or whatever you think is right. Anything above the cut point, that cut point or above is positives. Anything below are negatives. So finding a gold standard. So this is a little bit of the tricky part. What we found is that if we can create a noisy positive model, similar to what Juan did, that's probably good enough to produce the gold standard of positives. And what we call that is an extremely specific or expect cohort. And how we would build something like that, as an example for MI, we might take myocardial infarction and say we think a gold standard of people, a noisy set of positives, and noisy positives would be people with a very high probability of being positives, would be people who had 5 MI codes in their record. And MI codes would be something similar to what Chris built with his concept set definition using the myocardial infarction database, maybe taking out what we did here, maybe taking out old myocardial infarction, which is a child of myocardial infarction. So that gives us noisy positives. So positives that are very highly predictive of actually having the disease. So what we do then is we take those noisy positives, we create a cohort of the noisy positives, plus, like Juan did, people who did not have the condition at all. So we create a population of that, and then we run that through, we create as remember what Jenna was talking about yesterday, our T's, O's, and times at risk. Our T's are then, our target population is everybody. Our outcome are people who were the noisy positives. So then from there, we run the PLP package using and create a diagnostic predictive model. So now that model says, with some certain probability, these are the characteristics of people who have had this disease, myocardial infarction, for instance. Then we take 1 million random people, and we apply that model to those 1 million people. And from there, we have now 1 million people with a defined probability of having that disease, somewhere between 0 and 1. The next thing we do is now we start that. So that's our truth. That's what we're considering our truth. Those are the 1 million people with some sort of probability of having the disease. Now we start to create our test. Now we create our cohort, whatever you want to create in a cohort, and then we find the subjects in the cohort included or not included from those 1 million people, included or not included in the phenotype-derived cohort. Then we ask the question, were they included? So if they were included, we add the predicted probability to the true positive total. And if they weren't included, we add 1 minus the predicted probability to the false positive total. So it's like giving partial credit to your examination. Instead of a binary 1, 0, you're getting partial credit. So if you were predicted to be if the phenotype said this person had MI, and our probabilistic model said he had a 90% chance of having MI, then they get 90%, a 0.9 credit for getting it right, and a 0.1 deficit for getting it wrong. Same thing with the negatives. If you predicted somebody to be negative, the numbers are a little bit different, but just to go through the example, let's say that it was a 0.1% chance of being negative, which is really so 0.1 chance of being positive, which is, you reverse it, it's a 0.9 chance of being negative. So they would get 0.9 into their true negative column and 0.1 into their false negative column. And then from there, now you have totals for false negatives, false positives, true positives, and then you can run your calculations from there. So what you'll find when you start developing phenotypes is that there's a lot of standard ways to create phenotypes, and I used a couple examples here. One of those might be, if you want a very sensitive phenotype, you pick people who had one time of that condition. If you want to start to make things a little more specific, you might say you want one times of that condition, and then within 5 days, a second occurrence of that condition, maybe a follow-up condition. You might say, as some of the studies from Rubo had showed, that one times the health outcome of interest, but it has to be in an inpatient setting. You trust the inpatient setting. Or one times health outcome of interest in an inpatient in the first position, as that was the reason for admission. You really trust those. What we found is that we've done this for a number of different diseases. Number of different diseases: myocardial infarction, ischemic stroke, diabetes, atrial fibrillation. We've looked at the different algorithms that I've selected, that I just talked about. We compared it across 4 different data sets. So one of the things you see as the results is that the positive predictive value changes, even the same algorithm, but changes within the data set. And this is an important point here is that, so this is the CCAE data set, which is the younger people under 65. Medicare is people over 65. And one of the things you see here is that with that same algorithm, the one times health outcome of interest, you see a higher PPV in the Medicare than you do in CCAE. And that's true across the board. You see higher numbers here. And that shows you how PPV is a function of prevalence in the database. Because as you get older, unfortunately, we're not getting better, and there's more likelihood of having the disease as you get older. So you see a range, within the data set. So even if you use the algorithm and you took the PPV value from this clinical review adjudicated set, what's it really giving you? At the end of the day, you're really doing your testing on your own data sets, not the data set that they use to do their clinical review.
Joe, is the algorithm developed for each specific data set or in a combined data set?
You mean the phenotype algorithms?
Yeah.
Yeah, so it's the same phenotype algorithm. So for myocardial infarction, the algorithm would be, as you could have seen in Chris's outcome, where he looked at GI bleed, it was myocardial infarction, one time. Anybody with one-time myocardial infarction in their data record was considered a case.
And it is developed within the individual database?
Within the individual database. It's running, yeah. It's generated within them. Mm-hmm. The other thing you see is as the algorithms get more specific. So this bottom one has it's one times, but it's inpatient, and it's in the first position, so it's the primary reason for admission. You see that the sensitivity has dropped down significantly, so you've lost a bunch of people. You also see a range of the sensitivity. The positive predictive value, as you would expect, as things get more specific, positive predictive value increases as you get more specific with your phenotype. One of the things I want to point out here is that it's tempting when you're creating your cohorts and you're creating your phenotype algorithms to make very specific phenotype algorithms. It's like, I want to be doggone sure that these people have diabetes, really sure. So I might say diabetes, it has to be from an inpatient setting, and it has to be the primary reason for admission. But you see, if you do that, you see the sensitivity has dropped down tremendously based upon this testing that we're doing here. So now only, for instance, for CCAE, you're only getting 7% of the diabetics that are probably in your system. And the question is, who are those 7%, and how well do they generalize to the question that you're really looking for? So sensitivity becomes important with changing your algorithm. And that's why only having positive predictive value, which you generally get, is not quite the predictor that you want. So there are limitations to the system. You know, if you look at administrative data, you get sparse data in there, people with just a few records, and it's tough to tell, you know, from any of these machine learning algorithms. If you don't, it can only learn from what it's got. If it only has 100 different things in the data record, it can only learn from those 100 different things. Also, databases vary with overall detail and misclassification, and you know, so things, you know, so if there's high misclassification, you know, the machine learning algorithm is learning from a lot of misclassified data. And then if you look at your positives and negatives, there's maybes in the middle. So you have to consider, you know, what your cut point is going to be. The other thing to consider is that, you know, you think about some of the tests that I showed you previously. Catriona had said that 10% of their positives, when they went to review the case records with having all the data possible in the hospital with the folder that they had, 10% of the people the clinicians couldn't agree on whether they actually had a myocardial infarction. So, so that's one thing that you need to think about. So in conclusion, you know, having metrics for your phenotype performance, you can use those to increase your confidence in what you're doing. Have you gone too far with your specificity in your cohort, and that what you're getting here, your results are no longer generalizable. There are ways, and that's probably the next step for some of the stuff that we're going to be doing, to correct your output, your ends, and how many people have outcomes based upon using sensitivity and specificity. If you know the algorithm, if you know the performance characteristics, and you can then apply it to the data set. So we think that this use of diagnostic predictive models to assess algorithm performance shows some promise. We're doing additional testing. At some point, we're going to be bringing this out as a package within the OHDSI community. We want to do a few more things first to see how well this evaluates. You know, it goes back to what Juan said. You know, I might say it's 75% probability of this person having MI. Do we know that for sure? And we've looked at a couple different ways to do it, but you know, we're going to look at a few more. Yep.
So is the idea then, when you have a phenotyping library, that they would be validated, say for example, using this method?
You're right. So then you could have your phenotype library at your institution, use that, and then but also know it's just like, okay, these are the characteristics of this phenotype, and then let's say you have a phenotype library, and let's just say you have one data set that you're working with. This, you know, you have the Stanford data set, which is, you know, a big data set, and that's your only data set. Now you know for each of your phenotypes what are the performance characteristics on your data set, so you can adjust your results accordingly based upon that. Who else has questions?
I have a comment, it's not a question. You mentioned the chart reviews by physicians.
I'm sorry.
Chart reviews by
Chart
physicians.
reviews, yes. Mm-hmm.
Those were hard copies before, and there is not the time to do that.
Right.
But I wonder if there is a way to do this electronic chart reviews. I've seen on a platform, and actually it was pretty neat the way it was developed. It was easy to scroll and to follow quickly, and if you come up with certain criteria, it may take, like, I don't know, an hour maybe to review 12, 15 cases or even more if you have the true criteria.
Yeah, and well, the thing is that, you know, this is, so 2018 OHDSI, we talk about all the advances that we have. You know, sometimes when you look at the data, we're sort of, you know, almost in the Stone Age. And in a few years, when there's more and more electronic health records out there that has, you know, it's like, you know, Juan was talking about the data he has with clinician notes and measurements with actual values there that are well defined. I'm thinking like, oh man, that's a nice data set. You know, we have you know, insurance claims data. You know, we sort of look at the, you know, sometimes you can look at the measurements and sort of pick out values. But you're right, and notes are non-existent. But you have some of this stuff in the future, and all this stuff eventually will be going into the, you know, this algorithm, this machine learning can then pick up from that stuff and improve the performance as time goes on.
And there's the difference between infectious disease. I am in public health, so I work with CDC right now, and I've been in different places before, in different healthcare systems before. So infectious disease versus non-infectious disease. I can see that you can actually give up and you can say, if I have this number that I'm going to miss, if I'm using for something that will be applied onto some guidelines and policy, I'm still fine because the majority are still going to be included and I'm still going to, my results will be still meaningful. When it comes to an infectious disease, let's say if it's Ebola, God forbid some other kind of diseases, you don't want to miss any.
Right.
So I'm not sure if we're going to be able to look into in the future the differences between the meaning of, coming up with a way when you decide and you say this sensitivity, specificity, or this predictive value is good enough for me for whatever the scope is, versus just trying to reach a perfection because if I miss a patient, it's a problem.
Yeah. Well, at least you're getting closer to perfection, and similar to what Juan stuff does. So this uses all the characteristics. So somebody might have been miscoded for not having, didn't have the disease, but then they had an observation in the system that had it, that had some sort of inclination to this disease, or they had a treatment which was very specific to the disease. It's kind of amazing. I'm sort of amazed with misclassification on how much goes on, as in not, one of the things I was looking at was, as a measure of testing this, was to look at blood pressure. We happen to have an EHR set that we can actually get blood pressure pretty good. And I built an algorithm using blood pressure, a phenotype algorithm, where I said, they had to have 140 over 90, and they had to have it at 140 over 90 blood pressure a month later, and they had to have it 6 months later. So 3 different measurements of 140 over 90, and I also said you couldn't have any of less than 140 over 90. And I kept on coming up with a PPV of 90%. It's like, how is that? And it's like, how am I missing all these people? So I looked at the patient profiles, which is an aspect of Atlas. These people, they had 3 blood pressures of 140 over 90 or greater. They had no condition occurrences of hypertension. They had no hypertensive drugs on them. And it's just like, and it turned out, I did a review of about 100 patients, and I came up with about 90%. 90% actually had diagnosed with hypertension, and 10% did not have, even though they all had, so I was sort of amazed with that. So.
And then when we talk about applying to general population, we define in different ways. Like for instance, if you take Stanford, and I really love, what he presented, is a population at Stanford. If you take another larger group, when you have another type of EMR, and you do your analysis, it will be that population. When it comes to combine those, let's say I look at on a region, or I look to, I don't know, even larger population, all United States, how do you get it? Even if you apply this, it has to be a way when different things will merge, for the lack of a better word, together, or can be combined to make this kind of prevalence work, to find out an incidence that will have a meaning at another scale. And everything I heard, yesterday, it's absolutely amazing. It is impressive. And I feel like it's still a lot to do to combine all of this, but it's a brilliant group of people who can come up with these ideas of how to make this, at a larger scale.
Yeah, the nice thing about this is that you can apply it to all your different data sets with different prevalences, different things, and similar to what Juan's has. I mean, Juan can take you can take that Aphrodite and run it against your large data set and do something
and
very
we use
similar.
different platforms, and we used claims a lot before because we didn't have EMRs. We became experts, and there were many platforms developed. Some of them at the national level, it was very good to use. You have to know, but now it's time to look at near real time.
Yeah, you just mentioned if you develop the algorithm from one data set, and if you apply that to a different data set, you can expect to see different test characteristics, right?
Yeah.
Sensitivity, specificity, PPV could be different.
Yeah. And PPV is going to be the big one, because PPV is what people look at, as a quick reference. Of course, it sort of combines sensitivity and specificity, but like I said, the downside is it also includes prevalence. PPV changes with prevalence.
But you mentioned, like we saw in your data, that sensitivity and specificity sort of being a little stable.
A little bit, yeah. Generally more stable, but then again, you also have differences in the the quality of the data. Some data has better quality. Medicaid data has a little lower quality than Medicare data, for instance. I think that's my opinion.
And probably the evaluation of the phenotypes, if they apply to different data sets, have to go hand in hand with the quality, data quality assurance.
Yes.
With the features present in
That's
and
right.
the data missingness and all that.
And when you think about some of the stuff that Mark Suchard, and Patrick were talking about yesterday, the propensity score, which is using all the available data, you're getting what you're getting. So, you know, if it's a lower quality data set and it's there's fewer features in there, that is what it is. Okay?
Thank you. Thank you.